about image restoration. Okay, part 3 of the lecture, and the first section, that means restoration, finished, and we are in the second part of image restoration. Because the size was very big and the server couldn't upload it, I inflicted them to part 1 and part 2. This is the part 2 about image restoration. Okay, that's right. Digital image processing, image restoration, part 2. It was about inverse filtering. Okay, for image restoration. Inverse filtering is the deterministic and direct method for image restoration. We said about deterministic, non-deterministic, or stochastic methods, and we said about direct method and indirect method, for example, as learning methods. Okay, and we said about blind and semi-blind and non-blind methods. The image involved must be lexicographically ordered. That means an image is converted to a column vector, okay, by stacking the rows one by one after converting them to columns. Okay, are rows converted to columns, and columns are stacked over each other. Okay, therefore an image of size of, for example, m by n, or for example 256 by 256, is converted to a column of vector size of for example this item, 200 by 200 by 1. Okay, that means 4k by 1, no, 64k by 1. That's right. The degradation model is written in a matrix form as we had it: y was hf plus by n. Okay, in consistency of n, or if there wasn't any noise, we had y is hf. F was the input vector or image. Okay, the y was the blurred image or the output image or degraded image, and the h was the system or the degradation system. Okay, or blurring system, where the images are vectors and the degradation process is a huge but sparse matrix. Okay, of size mn by mn. We said about this sparse matrix. We had some diagonal matrices. Okay, in most of them we had 0 elements in rows and columns. Okay, but our diagonals, we had we had some items. The above relationship is ideal, but the true degradation model is hf plus by n, in consistency of noise. Okay, in existence of noise, where n is a lexicographically ordered two-dimensional noisy signal, which corrupts the distorted or blurred image y. F is input image and distorted in this system and tends to y, but applying by n, we have some another degradation, that means to y. We formulate an unconstrained optimization problem as here. We are minimizing j, for example jf. This is a norm of nf. Okay, or for example you can assume that the magnitude, okay, the magnitude of n, square magnitude of n. That means y is hf plus by n. Hf plus by n minus hf means n. Okay, this is the norm of n. We are minimizing this, and for minimizing or maximizing, we should go to this form. Okay, round the j to round the f is 0. This is for extremum, minimum or maximum point. Okay, but for reaching this J, we have some computations. This form y minus hf, y minus hf by 2 is y minus hf transpose dot y minus hf. Okay, this is transpose is applying in this parenthesis, means y transpose minus hf transpose. Okay, dot the second parenthesis, y minus hf. But this transpose, hf transpose, means f transpose h transpose. Okay, here this is y transpose minus f transpose h transpose dot the second parenthesis. That means applying this multiplication, we have y transpose y minus y transpose hf minus f transpose h transpose y plus y f transpose h transpose hf. Okay, and for example, we set the first derivative of jf equal to 0. Why? Because for reaching the extremum point or maximum or minimum. In this situation, for minimum. Okay, run the j to run the f is 0, means run to this item. Okay, run the y transpose y over f minus run the y transpose hf minus run the f transpose. All of them should be 0. Okay, and we know that run to run the f indicates a vector of partial directives. Okay, the derivatives, PDE. You know PDE, partial derivative equations. And run the y transpose y to run the f is 0, and run the y transpose hf to run the f is run the substituting here. Okay, is run the f transpose h transpose hf is y to run the f. Okay, and considering to this equation, we have this form. Minus 2 run the f transpose h transpose y plus y run the f transpose h transpose f hf over f is 0, and this item and this is 2 and removing, then we are here. H transpose hf is h transpose y. If the matrix H transpose H is invertible, then F is H transpose H inverse H transpose F here inverse H transpose Y. That's right. If H is a square and invertible, then F, what is F? F is H inverse H transpose H transpose Y. H transpose inverse H transpose is 1 or I. That means F is H inverse Y. This is an inversible system or reversible system. We had Y was HF, and here F is or F hat, an approximation of F. F is H inverse Y. If we don't have noise, okay, or the best one, minimizing this J. Salam Mrs. Dalla, salam Mrs. Dalla. مخلصين مشكلة نيست, no problem. That's right. Here, according to previous analysis, if H and therefore H inverse is Black's circulant, okay, the above problem can be solved as a set of m by n scalar problem as follows. F is H conjugate, all of them is in a spectral domain, okay. F is H conjugate, Y is output, okay, over H2. That means F in a spatial domain is inverse Fourier of this item, okay. H conjugate Y over H2. But H conjugate over H2 means over H. That means f is inverse of y over h. You know this item, okay? If we had a good system and a minimum, for example, contribution of noise, y was hf in a spectral domain, and f was y over h, and here f in a spectral domain is Fourier inverse of y over h. That's right. This is inverse filtering. Computational issues concerning inverse filtering. For example, for noise Fourier case, okay, this item that we said about noise Fourier. Suppose first that the additive noise n is negligible, is about 0, very small. A problem arises if h in a spectral domain becomes very small or 0 in some points where h was small. Here we had a h in the denominator, okay? If h was very small or about 0, what about this item, okay? It's very bad, and we are saying about it. If h becomes very small or 0 for some point u of v, for some frequencies, or for a whole region in, for example, UV plane, in that region inverse filtering cannot be applied, okay? Denominator over 0 or above 0. Note that in most real applications h drops off rapidly as a function of distance from the origin, okay? This is a very important problem. This statement is true because a couple of widely used degradation models are low pass signals, okay? For example, we had I disconnected the part of one. We had for example a rectangle window, or we had for example a circle window, okay, for blurring, and that means this is a low pass filter in UOV domain or in a spectral domain. If these points are known, they can be neglected in the computation of f. If the system was non-blind, and we, for example, are familiar with h, we can, for example, solve for about this problem in durations that h is small or 0. Okay. This for noise Fourier case. But for noisy systems, okay, for noisy case, in the presence of external noise, we have that f hat approximation of f hat is h conjugate dot y minus n, okay? Y was hf plus by n, hf plus by n minus n is hf, okay? hf dot h conjugate over h2. This is f hat, okay? F hat is h conjugate only hf over h2. That means is equal by dividing these two parts, okay? H hat y over this minus h hat n over this. That means is equal by, this is f itself, the input, h hat y over h2. This is the input version of image, minus n h hat over h2 is over h minus n over h, okay? If h becomes very small, we said about for some points, okay, in a spectral domain. If h becomes very small or about 0, the term n dominates the result. Some items over 0 is very large, okay, and for example some deviation about f hat from f. If as much h was very small, this term is the dominance. In the case, for example, in case H was small, okay? For example, in low-pass filters. For example, in Blur's we was saying. In that case, we have the so-called noise amplification effect. Okay, N over A small is amplifying noise. Noise amplification effect, where H was small or zero. And we are solving this problem in the next items. Okay, this is a bad item. This is amplifying noise effect. Okay. We have a solution: pseudo inverse filtering, not inverse filtering. Pseudo. Okay. What is pseudo inverse filtering for solving that problem, the noise amplification effect? To cope with noise amplification, we carry out the restoration process in a limited neighborhood above the origin where H is not very small. Okay? This procedure is called pseudo inverse or generalized inverse filtering. In that case, we said f a hat is H conjugate y over H2 when H was big or not zero. Okay, and f hat is 0 when H was 0 or very small. Okay, if we don't have this criteria, f hat was very big here. We say f hat is 0 when H was 0 for solving that problem. Okay, or f hat is y over H when H is, for example, greater than some threshold. Okay, for example, greater than epsilon, and is 0 otherwise. For example, if is very small, this item, not exactly 0, very small. Okay, lower than, for example, some dBs. That's okay. This is neglecting that noise amplification problem, or this is named pseudo inversing or pseudo inversing. For example, here you see a cameraman, okay, and blurred with, for example, this pillbox blur, for example, with 20 dB BSNR, blurred SNR. And another picture you see, for example, that picture cameraman, for example, blurred with Gaussian blur, okay, with variance of 1, and again with 20 dB BSNR. Here you see result of that picture is stored by a generalized inverse filter, okay, or pseudo inverse filter with a threshold of, for example, 1 over 1000. And you see ISNR is very bad. ISNR is negative. We had in the last session, ISNR negative is bad, and you see that you don't see anything. Its figure is worst, not better, after applying inverse filter. This is very bad, and this item is very bad compared to this one. Why? Because result of figure 5, for example, is sorted by a generalized inverse filter or a pseudo inverse filter with a threshold of epsilon is 1 over 1000 again, and you here see that ISNR again is negative. These two items are bad. Okay, but go to the next slide. The same input, but here you see the result is very good. Why? Because because using generalized better ones, okay, some XDB improving performance, or this one again, this item, and again with this threshold 1/10 for pseudo inversing, and you see again no, I say no, this is negative isn't good, okay, but this is very small negative, not for example minus 30 dB, okay, this is negligible, and you see again a good result, okay. That's right, this slide is very better compared to that one. That means by choosing a good epsilon, you can reach, for example, a good ISNR and a good result for the reverse system. That's right. In, for example, bad H, or in H in domains that H is very small or 0. Another one, or another solution, okay, and another improved solution. Constrained least squares, or instead of MLS, CLS, constrained least squares, or CLS restoration. By introducing a so-called Lagrange multiplier, or regularization parameter alpha, okay, we transform the constraint optimization problem to an unconstrained optimization problem, okay, as follows. What was the problem? Problem was minimizing J, okay. Salam Mr. Abbas. No problem. Minimizing J, or minimizing Y minus HF, okay, norm of Y minus HF. And we introducing CF, norm of we are subjecting CF, norm of CF smaller than epsilon, okay, some parameters. This problem is equivalent to minimizing J is that this J is Y minus HF plus by alpha CF2, okay. Here J was, for example, H minus Y minus HF plus by 2 plus by some items CF2, okay. When we was minimizing this item to, for example, smaller than some epsilon or some error, okay. That means this is equivalent by minimizing this item Y minus HF, okay, plus by alpha CF, norm of this item and norm of this item. In some regions we are minimizing this item, we said about, and in this some situations or some items or some for example areas we are minimizing this item, okay, and based on alpha. The imposed constraint implies that the energy of the restored image at high frequencies is below a, for example, threshold, okay. It's basically a smoothness constraint. What is CC? A high pass filter operator, and CF is a high pass filtered version of the image, okay. This high pass filtered should be, for example, lower than some thresholds here, lower than some threshold, or minimizing this item, minimizing this high pass filtered version of the input image. We formulate an unconstrained optimization problem as follows. Minimizing J means Y minus H2 plus by alpha norm of this item plus by alpha norm of this item, okay, and simplifying these items. This is this Y by conjugate, or this this item dot conjugate, or transpose dot it. That means Y minus HF transpose dot Y minus HF plus by this item transpose dot it. That means alpha CF transpose dot CF. We said this is Y transpose minus F transpose H transpose dot Y minus HF plus by alpha F transpose C transpose dot CF. Okay, and this is the that item. Again, we set the first derivative or run the F is 0, and after simplifying this item. Okay, and this is 2's are removed, and this item goes to this side. Okay, by plus sign, and means H transpose H plus by alpha C transpose C, all of them dot F. Okay, H transpose H F, alpha C transpose C F. Okay, FF here. This item is going here. H transpose Y. In the frequencies domain and under the process of noise, we have F hat. Okay, F hat is the output of the reverse system. F hat was H conjugate Y minus N over. In the first time we had only H2. Okay, but this time we have in the denominator H2 plus by alpha C2. Okay, this is the for example improved version of the inverse system. Okay, or the reverse system. H is 0 or very small in some items. Okay, if we didn't have this item, this small item was a bad point. Okay, but because we have this item, when this was 0, this is applying. Okay, this is working, this item. Oh no, what was this? Okay, I stop sharing and go share my screen. You see this we was here. Okay, we was here, and this is the corrupted page, and this was okay. I'm discussing this item. Some observation for CLS. Okay, constraint list squares. In frequency domain and under the presence of noise, we had this item. F hat was we said this item H conjugate dot Y minus N over H2 plus by alpha C2. Okay, for regularization parameter alpha controls this parameter controls the contribution between Y minus H2 HF2 and CF2. Okay, some balancing between this right. A small alpha implies that emphasis is given to the minimization function of this item. Okay, if alpha is a small, this is 0, and this is, for example, highlighted. Okay, if alpha is large, this is, for example, 0, and this is highlighted. Okay, a small alpha implies that emphasis is given to the minimization function of H minus Y minus HF2. Note that in the 0, this is an anyone. This is the last item. Okay, last problem. CLS becomes inverse filtering itself. Okay, not improving inverse filtering. Note that when with a smaller values of alpha, small, not 0, the restored image tends to have more amplified noise effects. Okay, it said this is, for example, bad. This is highlighted, and this is, for example, negligible. This is bad and noise amplified filter effects. Large alphas implies that emphasis is given to the minimization function of CF2. Okay, in where h was 0 or was bad. Okay, we choose alpha large. A large alpha should be chosen if the noise is high. Okay, the second item here, this item, our small item or 0 is very bad. In these times we choose alpha large. Note that with larger values of alpha and thus more regularization, the restored image tends to have more ringing. Okay, some ring effect. And we are here, but because of the bandwidth, I go back to the file. Okay, stop sharing, and I go back to share document, restoration 2. Here we said about that item, and here because about choosing alpha 0, alpha small, and alpha large. Okay, we had some discussion about these values of alpha. The problem of the choice of alpha has been attempted in a large number of studies. Okay, and different techniques have been proposed, for example, in some papers. One possible choice is based on a set theoretic approach. Okay, set theoretic approach. A restored image is approximated by an image which lies in the intersection of two ellipsoids, means this item. Okay, we say in Persian vis-a-vis. Defined by, for example, QFY is H when Y normal Y minus HF is, for example, smaller than E2, and QF is when F when norm of CF is smaller than, for example, some errors epsilon 2. The center of one of the ellipsoids, which bounds the intersection of QFY, QF if Y, and QF itself, is given by this equation. F is H transpose H plus by alpha C transpose C inverse H transpose Y. And here, what is alpha in this item? Alpha is E over epsilon. Okay, part by 2 is a good choice, for example, if we had alpha E and epsilon. Finally, a choice of alpha, for example, is also 1 over BSNR. In for example, almost items, we have BSNR. This is a very good choice. Alpha is a good choice for to chosen as 1 over BSNR, for example, in DV. Again, the variance and bias of the error image in frequency domain are here. Variance of F hat, okay, is variance of noise, sigma over our items in spectral, U and V, H2 over H2 plus by alpha C2. Okay, all of them part by 2. This is variance of F. And mean of F, or bias of F, okay, F hat, is again variance of or energy of noise and sigma over all pixels, okay, n by n. This is for mean. F2 alpha 2 C4, that means F alpha C2 divided by 2, all of them, again, or H2 plus by alpha C2, all of them by 2. This is variance and mean of F hat. Note that the mean squared error E or E alpha in this problem is the expected value of the Euclidean norm of the difference between the true original image F and the estimated original image F hat. That means E or expected value norm of F hat minus F. Okay, this is MSE or mean squared error. It has been shown that the minimum mean squared error in this slide, solid. this item. Okay, this item. This is minimum square error. Is encountered close to the intersection of the above functions and is equal to, here in this expected value of mean square error is mean plus by variance, or bias plus by variance of f hat. Okay, that means observing that graphs for the variance and bias of the error in the next slide, we can say that another good choice of alpha is one that gives the best compromise between the variance and bias or mean of the error image. This is a very good slide. This item. What alpha is good or good choice? Okay, increasing alpha, you see that variance is decreasing. Okay, variance is decreasing, but mean is increasing, and MSE, mean square error, what was the add of these two items? Okay, jam of these two items. And what is the best point? This point is the best point, for example, or this area is the best point. Okay, for example, for this item, for example, about 1/10, 100s, these items. Okay, for example, this slide or this example. Again, cameraman ruled by, for example, this formula pillbox with, for example, this PSNR 20 dB, and choosing alpha 1/10,000. Okay, a small alpha. This is this item. This alpha, and again this alpha for these two sides, 1/10,000. This is about here, for example, this item. Okay, and this is about here, and you see that the result is bad. Okay, result is bad, and you see ISNR, for example, about minus 20 dB. Okay, and this is about again minus 20 dB, 22 dB. This result is bad. That's right, because a bad choice for every. But go for the if alpha is very small, H2 in the denominator is highlighted. Okay, and again this is inverse, not pseudo inverse, and this is a bad CLS or a not working CLS. Okay, constraint. But in the next slide, a better choice for alpha. For example, alpha is 10 powered by 0, 1, this item. This is alpha is 1. Okay, this is, for example, here is very better than, for example, here. Okay, about these items here, these items dB in performance degradation, or for example here you see alpha is 1 and you have a positive ISNR, for example, about 2 dB or 2.5 dB, improving the picture compared to this one. And here again with alpha 1 you have, for example, about 1 dB compared to this one. Okay, a good choice for alpha, and the last slide, a bad choice for alpha, for example, here. Or again I stop sharing, I go for screen share here. Here, the next one, Wiener filtering or Wiener filter estimator. Okay, here we have a stochastic regularization. Okay, the image restoration problem can be viewed as a system identified problem as follows. We had the input image f applied to degradation system, and maybe adding some noises to it, n. This is the y, the output blurred or degraded image, okay, degraded image. And this is the inverse system or reverse system we are finding, okay. And here we name is W, Wiener filter, okay, and the output named f hat, okay. The objective is to minimize the expected value of the Euclidean norm of the error of f hat dot f minus f hat transpose dot f minus f hat, okay. This is the norm of f minus f hat, okay, or this is norm of error between output, restored output, and the original image f minus f hat, okay. This is norm of this difference and expected value of it because of a stochastic problem. To do so, the following conditions should hold. 1. At b expected value of f. That means expected value of f, b, or w expected value of y. This is y, and because of stochastic, expected value of y dot f. This is very good. Expected value of both of them is the same, and minimum error, okay, between these expected values. Another one, the error must be orthogonal to the observation about the mean. Observation about the mean. That means expected value of f hat minus f, y minus expected value of y. This is y. This is mean, okay. Mean of output y minus expected value of f hat minus f dot this for example, this deviation or variance, okay, variance transpose is 0. This expected value is 0. It means orthogonality, okay. The error must be orthogonal. Orthogonal means expected value of this item dot this time is 0. That means the error must be orthogonal to the observation about the mean. This is observation about the mean, y minus expected value, or y minus mean of y. We say the version انحراف معیار or square root of variance, or deviation. Deviation means that's right. We set these two criteria in the last slide, okay. From I and 2, we have that expected value of wy. W was a winner, okay. This is wy, okay. W is the reverse system. Expected value of wy minus f dot انحراف معیار y minus expected value of y transpose was 0, or should be 0 for a good sense, okay. That means substituting, for example, wy minus here is minus f, okay, and plus and minus these two items. These two items are the same, plusing and minusing, okay. Expected value of f minus w expected value of y. These two are the same, okay, and differentiated it, okay. This item and this item is this and this, okay. Dot this item dot this enhancer transpose, okay, is 0. Why added and subtracted these two items? Because of this the next one. For example choosing some items. Okay, means is equal by expected value of these two items, w dot y, w dot expected value of y, w dot y minus expected value of y, minus, here is f and here is expected value of f, minus f minus expected value of f dot y minus expected value of y transpose. Okay, again the same. If you say y hat, for example, is y minus expected value of y. Okay, this is n harf mayor of y, and we say f hat, for example, minus expected value of f, we have expected value of w y hat minus f hat. This is y hat n harf mayor. This is f hat. W y hat minus salam مسائي w y hat minus f hat dot, this is this item is again the y hat. Okay, y hat transpose is 0. Okay. And going to the next side, that means w y hat transpose. Okay, expected value of w y hat transpose is equal by next side, expected value of here is plus f hat y hat transpose is equal by expected value of f hat y hat transpose, and this item is going outside w expected value of y hat transpose, because this system isn't stochastic. This is a system. Okay, defined norm system. W expected value of y hat transpose is expected value of f hat y hat transpose. But what is this item? Y hat transpose is auto-relationship. Okay, or correlation. W autocorrelation of y or y hat. Okay, or an mayor of y is this is cross correlation. Okay, f y transpose. This was y transpose is autocorrelation. Okay, and f y transpose is cross correlation between f and y. Okay, go next slide. If the origin and the degraded image are both zero mean, then autocorrelation of y is autocorrelation of y hat. Okay, autocorrelation of y hat is autocorrelation of y itself, because zero mean, and fy hat is cross correlation of fy, again because zero mean of both of them. Okay, in that case we have that in this item, not hat, w autocorrelation of correlation of f of y. W is the Wiener system. Okay, or Wiener filter. If we go back on the autocorrelation matrix of the degraded image, then we get that y was hf plus by n. Okay, and y transpose was f transpose h transpose plus by n transpose. Okay, and expected value of y transpose is h autocorrelation of f. Okay, here y transpose, this is y transpose. Y transpose expected value is this was f transpose h transpose. Okay, this is h autocorrelation H transpose, autocorrelation of plus by autocorrelation of noise. Okay, and this is autocorrelation of output. Autocorrelation of output noise plus by H transpose dot autocorrelation of input dot, and for cross correlation expected value of Hy transpose is autocorrelation of H transpose. We have Fy transpose, that means cross correlation of Fy is autocorrelation of input dot H transpose. From the above formula result, W, the winner system we are find U, is cross correlation of input and output and cross correlation of output inverse. Or substituting these items, okay, we have is autocorrelation of input dot H transpose dot H autocorrelation of input H transpose autocorrelation of noise inverse. The estimation for this winner system or winner filter, and estimate for the original is, what about F hat by this? F hat is U dot Y. Okay, F hat was W dot Y, and this item autocorrelation of input H transpose H autocorrelation of input H transpose autocorrelation of noise inverse dot Y. So that knowledge of autocorrelation here in this formula, to have these items we should have some this is a non-blind. We should know about autocorrelation of input and autocorrelation of noise. Okay. In frequency domain, W is PSD of input or power spectral density. Okay, power image dot H hat or H conjugate of input dot H2 plus by PSD of, okay, and F hat is PSD of input dot H hat H conjugate input image dot H2 plus by PSD of noise all of them dot Y. This item SFF is PSD of F input image, and SNN is PSD of power spectral density of noise. Counter issues, the noise variance has to be none. We said non-blind. Okay, we should know about, for example, PSD of noise and autocorrelation of noise and variance of noise. The noise variance should be known, otherwise it's estimated from a flat region of the observed image. If we didn't know the noise variance, okay, these items, it's estimated. We can estimate from a flat region of the observed image. Okay, from some item in our image, we can, for example, estimate about the noise. In practical cases, where a single copy of the degraded image is available and not some streams, it's quite common to use SYY or PSD of output as an estimate of PSD of input. Okay, PSD of output is the same as PSD of the input image. This is very often a poor estimate, not a good estimate. Maybe PSD of output doesn't mean the PST of input. But in some items it is a good criteria, maybe. And again, in the absence of any blur, a good system, H is 1, okay? The input is transferred to the output. And we have this item. W is PST of input over PST of input plus by PST of noise. Dividing by these two items, numerator and denominator, dividing by SANN means PST of input plus by PST of input over PST of noise plus by SANN over SANN or plus by 1. What is this? Input image over PST of noise. This is SNR, not BSNR. In this system we have H is 1. This is SNR, image ratio. And again, SAFF over SNN, PST of the image over PST of noise, again SNR. SNR, signal to noise ratio, over SNR. This is W, okay? Or winner system. But we say about these two items. If SNR is very small, for example, compared to 1, compared to this item. If SNR is very large compared to 1, and SNR over SNR is 1, okay, W is about 1. But for example, if the system was very noisy, very small, noisy, okay, invisible, and W is SNR, okay, W is SNR. If system was good, a good peak W, a good winner system, okay, or a good winner filter is 1. If we have some noisy picture with very low, a good estimation for a good winners filter is SNR itself. SNR is high when in low spatial frequencies. For example, when your camera isn't moving, okay, means low spatial frequencies. If you have a constant camera, this is a low spatial frequencies, and low in high spatial frequencies. Low pass filter, a smoothing filter. Using a low pass filter, you can, for example, estimate a good winner filter. That's right. Why? Because of these two items. And the last slide for this part 3 for restoration is the last slide. Relation of winner filter with inverse filter. We said about inverse filtering, pseudo inverse filtering, or adding CLS, okay, and after it we said about winner filtering. What relation between winner filtering and inverse filtering? If PST of noise was 0, winner filter is H, okay, here, for example, winner was here, okay, W was PST of input, H conjugate over PST of input, H2 plus by, if PST of noise was 0, this item is 0, this item by this item is neglecting, okay, and H conjugate over H2 is 1 over H, this item. If we didn't have any noises, okay, we didn't have any noises, PST of noise was 0, the inverse of system, reversing system, a good reversing system is exactly the reverse of the degrading system. Okay, 1/h, which is the inverse filter relation. If we didn't have any noises, winner is inverse, the inverse filter. Okay, but if we had some noises, but some small noises, PSD of noise is about 0, small. Okay, W is the total item. PSD of input and this item. Okay, this W tends to this item. Limit of noise is tending to 0 is all H's. Okay, means inverse of an inverse filter for H is 0, a small h. Okay, it as 0. That's right, 0. This item, for example, h is 0. This item is 0. Is 0. This is negligible. This item, SAF, F foot, H conjugate over PSD of noise. Okay, and we can say this item as okay. This is pseudo inverse. Okay, we have in last slides. If, for example, we didn't set this is 0, we had the effect of amplification of noise. Okay, this SNN is about 0, and is very some items. Our small item is very large and is very bad. Okay, this is 0 in this item. In these situations, we select is as for solving problem and name it pseudo inverse filtering. That means the winner filter can support both of them, both of inverse filtering and pseudo inverse filtering. That's right. Inverse filtering in other areas and pseudo inverse filtering does. And this is the completeness of this part. Inshallah, in the next week we inshallah I upload this restoration to subtraining, and this is Maryam. Salam. Salam. I upload this file for you. I checked it and it was about 7 megabytes. Okay, and this server have a limitation of 5 megabytes. Maybe I have to, for example, segment this restorator to 2 segments, maybe. Okay, and this is the fullness of part 3, and the next week we go to part 4 for comparison and for starting our projects. Okay, maybe the first project in the next week. Maybe 4 projects. Okay, project 1, 2, 3, 4, 5. Maybe each of them about 4 scores, maybe, and a final exam about, for example, 5 scores or 4 scores, or between 4 to 6 scores. Okay, some projects with a smaller score final exam. That's right. All of the project in MATLAB. There's any question? مخلصون. Okay, I share this document for the last slide, that for I know the end of this class. Okay, this was for here too. I know that we completed this file. That's right. خدا حافظ همگی. خدا حافظ جمیعا. That's right.